I'm Arash, and we're going to talk about the second part of strengthening of reinforced concrete structures using fiber reinforced polymer composites. So again, as always, there's the outlines, and let's begin by recapping on some of the stuff that we learned during the first part. If you remember, the majority of the first part were concentrated on the strengthening of beam as well as what FRP is in terms of material and in terms of its advantages and disadvantages against some other strengthening methods like bracing, shear walls, concrete jacketing, steel jacketing, base isolators, and dampers. Now, one thing that we learned in the previous part 1 was that the direction of the FRPs and the fibers of the FRP sheets are very important, and they play a major role in resisting different loads. We said whenever we want to resist the flexural or the bending moment, we put the FRP's fibers in the same direction as the longitudinal reinforcement of the section. This is the cross section. As you can see, these small dots are the longitudinal ones. And if I look at the side, you can see that if these are the, let's say, the direction of the reinforcement, the fiber's direction is in the same way as well. On the other side, remember that FRP only had elastic behavior and it was only in tension, no compression resistance at all. That elastic behavior was very high elasticity, high final strength as well, but when it reaches to its ultimate point, there was a sudden rupture because it's only elastic. It does not have any nonlinear, plastic or ductile behavior. The same thing applies for the shear as well. If the shear reinforcement goes along and around the longitudinal reinforcement to hold them together, which we sometimes call them ties, struts, shear reinforcement, the same thing happens to the fibers of the FRP as well. As you can see, they go up to down or like this. Similarly, in the column as well, depending on how we want to resist the different types of loading which are applied on our column, which usually are axial, bending moment, as well as shear, the direction of the fibers play a very important role, and we will talk about it in more detail, so let's keep it for now. Getting back to the strengthening of our C-beams, we said that if our section is reinforced with fiber reinforced polymers, there will be two types of failure. We either will have a failure due to the concrete, which the concrete had reached its compressive strength, this top bit, and the concrete has failed. Again, remember, concrete is very good in compression but it's terrible in tension. That's why we use the FRP or we use the steel rebars to improve it in terms of tension. Now, it's either the compressive strength has reached in terms of strain and the concrete has given up, or the FRP tensile strain has reached. So if this is the compressive bit, this is the tension bit, the FRP has reached to this strain. So either of these can happen, and accordingly we will do the calculations. The calculations weren't very sophisticated. It was just simply doing a section analysis of an RC with the difference of having an added piece of FRP at its bottom. As you can see, the FRP will have a thickness as well as the FRP had an area, which both of these were coming into effect in the formulations. First, we were finding the neutral axis, and then using that neutral axis, we were getting a bending moment along any point. For example, we were taking it along the point of the steel in tension. Having that, we were calculating the capacity, the moment capacity of our section when the FRP is present. With this, we were comparing it to the applied moments, so getting the results out of the analysis of Oasis GSA, Seismostruct, ETABS, SAP 2000, robots from Autodesk. Any of these softwares were giving us the MED, what is applied to my structure due to the dead loads and live loads and lateral loads and wind load and stuff like that. And then if I calculate the resistance of my moment, resistance of my concrete section, that should be higher than the applied one. Then everyone would be happy, and your section retrofitted with that FRP is sufficient to resist that bending moment. Very similar to the bending moments, we had an easier section for the shear enhancement of RC beams. Again, pay attention how the direction of the fibers in the beam are situated. It follows exactly what happens in the struts or the shear reinforcement of the section. This was similar with the same concept as well. So the resistance of the section after the FRP was added should have been higher than the applied shear. And this resistance was simply a minimum of all the shear in tension, meaning the steel as well as the FRP, these guys who are responsible for saving our section against tension forces, as well as the shear in compression, which was due to the concrete. Each of them had a formula. If you calculate them, the summation of the tension one and the compression of the concrete, the minimum value will be the resistance that you have in your section. You were comparing this to your applied loads, the shear of the applied loads, and if it was satisfied, your, let's say, enhancement, your strengthening method is acceptable. So this was a simple recap of what we did in the previous one, but now let's pay attention to what happens in an RC column. Over here we have an RC column. You can see it's set. These are some properties of that section. We're applying an axial load and we want to see how it reacts under our actuator, which is loading it from the top and the bottom. You can see the bending, you can see the deformation, the proper buckling of your column. You can see how much non-linear behavior the steel has, the shear reinforcement has, the core of the concrete and the covers. Let's slow it down and see what happens. So definitely a failure of the cover. This is an unconfined concrete. We carry on with the loading, more axial load, more axial load. You can see the bits and pieces are getting separated. You can see the cracks are getting bigger and bigger. Now you can really see the core of the concrete. Now we should be able to see the steel reinforcement because the cover is gone, as you can see over here. The longitudinal steel reinforcement as well as the struts or the shear reinforcements are coming out. And this is a simple stress versus strain, which we can convert it to axial load because stress is force over area, as well as the strain, which is the vertical deflection, or in a normal situation, strain is change of length over initial length. You can see the graph can be plotted and we can figure out what is the capacity of our section. Now, out of that demonstration, the most important bit was to understand how a column reacts under different loading. So the column can fail in either of these three situations. It will either buckle, as you can see here. You can see the buckling of the steels as well, and this buckling will push all of the transverse reinforcement or the shear reinforcements away from that stomach, and then the core concrete will be loosened and it will lose its old strength. The other situation is that the axial load on top of your column, imagine this is a pier of a bridge, and then suddenly instead of one truck, which you have designed your bridge to withstand, is now two trucks. So your column is now under so much pressure, it has pure axial load on it without any eccentricity, without any lateral load, so it just goes zoop, all goes down, and then this will cause a proper stomach in that section. Similarly, if you remember the Samurai Kid, if the Samurai Kid just cuts my section, which as you can see usually is due to a lateral force like earthquake, that lateral force can cut my whole section like this, kind of perpendicular to its surface, and that would be the shear. So these are the issues that we have in columns, and we want to see whether FRP can be a solution for them or not. Let's see some more examples of compressive, which the actual is great. You can see a very good distributed, evenly distributed damage to the entire column. You can see the stomach of the reinforcement. You can also notice that apparently the spacing between these transverse reinforcements, which are supposed to hug the column, are a little bit too much, maybe a little bit bigger than what the code suggests. That's why they're getting the stomach. Imagine if there was another one of these struts in middle of these two struts. For sure this failure would not have happened. Similarly over here as well, in this case you can see the longitudinal reinforcements are completely given out as well. Let's look at some shear cases. You can see a clear shear case. These are all due to the earthquake. This is a very unusual case because you see this bridge should have probably followed the other adjacent bridge beside it, but not only it got compressed, it also had an unusual torsional failure. You can see that it has twisted along its center. So yes, FRP is one of the solutions that we can improve the ductility, the axial capacity, and the flexural strength or capacity of our columns. By applying FRP, we can improve some additional confinement to our column, which that confinement increase will also result in a better ductility as well as a better axial capacity. We will define and we will discuss confinement in few slides. FRP will also increase the flexural strength. Now pay attention that the direction of the fibers in both cases are very important as well. So in this case that the fibers are going from the bottom to the top of the column and they follow the longitudinal reinforcement of the column, they're actually improving the flexural strength in terms of the tension side. When the fibers are in this direction that they kind of hug the column, and they go around the cross section, they're actually acting as the shear reinforcement or the ties or the struts or the transverse reinforcement. So they're actually increasing the confinement, which as a result, the ductility and the axial capacity will increase. The testing that whether you need FRP and whether there is any issue in any terms is very similar to what we did with the beam. So you just test the capacity or the resistance of your section in terms of flexural, in terms of shear and confinement, and as well as the axial against what is applied. Now pay attention that over here in terms of the flexural retrofitting, which is the bending moment, the capacity of your column should be always higher. This is the case that we need the flexural retrofitting. What is desired is that the summation of that capacity of your column is always higher than 1.3 times the summation of the new moment capacity of your beam. This is to make sure that the capacity design is applied. The capacity design, if you remember, was that chain, and we were saying that in a chain, if we pull it from both sides, the weakest link will always fail first. Now we apply the same thing in the building. We identify the weakest link, which for example are the beams in most cases, and we make sure that they act ductile, they act inelastic. So when the earthquake strikes, they start dancing and they deform and dissipate energy and get rid of the massive lateral force of the earthquake. Now the other links of the chain and the other components of my building, like the columns, like the connections, like the foundation, should be stronger than that weakest link, which was the beam. So if we design them in an elastic way, but we make sure that they are stronger than the beam, then everything will be fine. And by this, we will avoid soft story failure, as well as having strong beams but weak columns, which is not desirable. On the other side, the FRP retrofitting will prevent the lap splice failure, which, as you know, for example, whenever two reinforcements from different components, in this case the footing, is coming inside the column, and this is the way that we connect these two components to act as a system together, there will be some spacing, which we call it the lap splice. The code has some dimensions for it, but failure usually happens over there massively because these are two different reinforcements just coming and they're just tied together with very thin steel material. So the FRP can improve that issue of their failure. On the other side, due to some lack of proper detailing, the rebars might buckle, specifically at the ends of the column. FRP can improve that issue as well as the flexural, the shear and confinement, and the axial issues that the column might have. I have been talking about confinement a lot, so let's just concentrate on confinement. Imagine this is your shape, imagine this is your column or any component of the structure. For sure, if I just apply axial loads, like compression in this case, so the top force and the bottom force are just coming together, for sure the shape will start moving to the sides and it will reduce its length, but it will increase its cross-sectional area. Now, if these red arrows are my resistance or my confinement, that confinement resistance will make sure that this column does not change in terms of cross-sectional area and it keeps it in its own position. Otherwise, the shape will give up, and as you can see, the length will be reduced. So this is simply confinement. Now, confinement in columns and generally reinforced concrete columns is a very important thing, and the higher you have in terms of confinement, the higher strength you will have, as well as a better ductility you will have. This is a very nice stress-strain relationship of a reinforced concrete column. As you can see, if it doesn't have proper confinement or it's unconfined, this is the strength, the ultimate strength, and this is the ductility. So if this is the yield point, let's say at this point, ductility, if you remember, was simply the last ultimate strain ratio against the yield point. As you can see, it's just this guy over this guy. Now consider that we have added confinement by adding reinforcement that we will discuss in a second. Now if this is the ultimate strain that I have, the ratio between this point and this point is much bigger than this point and this point. So we are getting the ultimate against the yield, and that will be our ductility factor or ductility ratio. You can see that the confinement will increase the ductility of your section. That is heavily desirable under heavy and extreme lateral loads like wind and earthquake. This is how we dissipate energy and we make sure that our structure is sound, and it gives enough time to the residents to jump out of the window, to get out to the fire exits and get out of the building. We don't want a very low ductile structure or a structure which suddenly collapses, like a brittle collapse, like glass, what happens in glass. We don't want that, and we want to avoid that. On the other side, you can see the ultimate strength has improved massively as well. Now this is a good 3D schematic of what a confinement can do. The gray bits are the bits and pieces of the concrete which are supported in terms of confinement, so they won't change in terms of area. This is in a normal situation that you have just some reinforcement, shear reinforcement with some spacing. You can see that the 135 degree of closing these ties are at least applied. There is another schematic of it. Now an improved way is to have a little bit more, some more legs. If you remember, we were counting the legs 1, 2. In this case is 1, 2, 3, 4 legs for the shear reinforcement, and then you can see we have added some shear reinforcement in the middle as well. You can see the confinement has improved massively. Now remember, the cover of the concrete is always unconfined because we don't have anything around it, while the core of the concrete, which is in the middle of the shear reinforcement, is always confined. Now imagine if I put FRP around this, then the cover will be confined as well, and then all of these additional reinforcement will increase the confinement factor of your section, which as a result will increase the strength of your section as well as the ductility of the section. Let's look at some experimental results. Over here we have load versus strain, so change of length over initial length. I have an unreinforced concrete, very low ductility, very low strength, and I have 4 different types of let's say reinforcement in terms of shear and confinement. For sure BP12 is the weakest one, then should be the D10, 16D10. You can follow it on these, so let's call it BP12 and S06. You see BP12 and S06, give or take, they have kind of similar, depending on how many reinforcement they have, ductility as well as strength. And then the ultimate of these should be M12. As you can see, lots of legs, lots of reinforcements, not only in longitudinal but also in the shear. And yes, M12 has the highest ductility as well as the highest strength. M12 is the dashed line. You can see it's on top of everything. So for sure, having lots of reinforcement over there is good, but remember, there's always a ratio. Too many of these reinforcements means that less concrete will be in the middle. Remember, the steel is there to improve the tensile strength of the section. If you have too little concrete, then your compressive strength will be reduced, which can cause much more problems than the tensile bits. And on the other side, making such thing takes long time, is very labor intensive, as well as you buy steel in terms of tonnage, how you weight the steel. So the more steel you have, the more expensive it will be. So the cost is an issue as well. Okay, let's quickly go through some benefits that confinement will bring to our reinforced concrete column. For example, as we discussed, it increased the ultimate capacity, it increased the capacity of a member which is under combined bending moment and axial load. This usually happens when the loading, the axial load, the compressive load, is not at its center of the column. This happens a lot in bridges. Imagine you have a bridge with the cars are passing in the middle, so the axial load is actually in the middle while the columns are on the sides of the bridge. So there is a distance between that axial load and your center of your column. That distance will cause a phenomenon called, for example, P delta, and it will cause a moment on your section. That will be improved by adding confinement. We will discuss about this in the coming slides. It will increase the strain of the member, and as a result, it will increase the ductility. As we discussed, it will increase the bond length at lap splices. So this failure, as well as it will delay the rebar buckling. So confinement is very useful, and as a civil engineer, as a structural engineer, as an earthquake engineer, we have to always make sure that our columns have sufficient confinement under any circumstance to withstand any lateral loading which will be exerted on them. So as a summary, it just increases the strength capacity as well as the deformation capacity because it increases the ductility. Some examples of those rebar bucklings, as I mentioned, it usually happens at the ends of the column where the column is connected either to the slab or the beam at the top or the bottom. As you can see, local bucklings in the longitudinal reinforcements. This can be easily solved by adding FRP, as well as the lap splices that we discussed. Over here you can see probably some of these reinforcements are coming from the floor or coming from the footing, and a proper failure has happened. This distance between two reinforcements which are getting connected has a proper standard in the code depending on what you're designing. Now let's see the confinement effects when we're just adding the thickness of our FRP. So we have one unconfined concrete, which, as you can see, the ultimate strength is over here, and by getting this over the other one, you can kind of find the ductility in terms of strain. So ultimate strength over the yield strength. Now I have 4 other FRPs which have increased the confinement of my concrete section, and as you can see, they're increasing in thickness. As you can see, as the thickness increases, the strength goes higher, as well as the ductility goes higher. So remember, the FRP, the more thickness you have, or when you increase the thickness, you're actually adding more layers. If one layer is, let's say, 0.15 millimeters in terms of thickness, if you add 2 layers, then you have 0.30. Then you have increased the thickness of your FRP, and as a result, you have better strength and better ductility. So ultimate strength of confined concrete is now FCC. Remember this. And epsilon cc is the strain of confined concrete at ultimate strength. So now we're dealing with a new type of strength which has confinement in it. That's why we have double C's over there. This FCC is equal to the same. So we discussed that the highest number of stress is actually called strength. And talking about what we just discussed, for FRP jackets with equal stiffness, you see the stiffness of all of them are the same, and different thicknesses, as you can see, FCC increases with epsilon FUE. The strain of fiber at ultimate strength. Yeah, it increases. For FRP jackets with equal thickness, now we're not increasing anymore, but different types of fibers. So now we're changing the fibers. We're going from, like, for example, high strength carbon or high modulus carbon to glass to basalt to aramid. The FCC increases with FFDE, the ultimate strength of fiber. So the higher the strength of your fiber is, the total strength of your ultimate confined concrete will be increased as well. The same thing happens with the strain as well. If the strain of your fiber is increased, the strain of your system, the confined system, will increase as well. So repeat these to fully understand that's how they act. And the design model generally for confinement is very simple in terms of the actual load and the confined actual capacity. As we discussed, the applied should always be lower than the capacity or the resistance. Now pay attention that this NRD has now changed to NRCCD, meaning the confined concrete resistance. And as long as that is higher than your applied load, which is due to your dead load or live load or whatever you have on your structure, like lateral load, then you have done a good job. The confinement is not necessarily just straight fibers. It can have some angles as well, and we will discuss this and how they affect on the design as well.